welcome to ME 212 Robust and Optimal Control. This is a new course we started this fall semester of 2019. It's for the first time offered on this campus. So you guys are part of the history, okay? Part of history. So we went through W1, 2, 3, 4, 5, 6 were here. And today we are going to discuss mainly on balanced model reduction. So first of all, we need to set up the stage about why we need to even talk about this, okay? All right, so we know that we have a plant P here, okay, or P here, and we want to control it. This is our real plant, I want to control it. Whenever we see the plant, so we know that the P is a nominal model plus delta P. So the delta P is called uncertainty. I want to tell you today that the uncertainties comes from two directions. One is because we really do not know. Okay? We really do not know. Okay? Another part of this uncertainty is from that we actually know. Okay, we see we actually know, but prefer to ignore. Okay? That makes very good sense because sometimes the model you use is just too complicated. Yes, it's very accurate, but it's too complicated. I purposely want to have a nominal model and put that one. Let me give you one example. Say, for example, okay? For example, I have a slowly time varying nonlinear system, okay? So you say, for example, like oil refinery, like, you have a lot of complicated factors. They change slowly. It's not like an abrupt change, slowly. So I really hope I can have a nominal model that P naught is LTI, linear time invariant. While my delta P will count for those non-linear time varying effects. Okay? Okay? And even though we know, so we purposely do that. So if somebody said, oh, you learn a linear control, MIMO linear control. And you said, oh, what are you talking? So we learn about a lot of linear time invariant systems. And so you said, oh, you cannot do any real world system controls, okay? But you say, oh, by the way, we also learn robust control. Okay? Then you are a step closer to reality because in reality, those nonlinear effects, those time varying effects still can be considered. We just extract those LTI, okay? And I treat all others nonlinear and time varying factors into the delta P on purpose. Okay? So this is called ignore, this is called on purpose. Okay? Make sense? That's one example. Another example is I have a P but it's too high an order, too high an order, okay? The order is just too high, it's too big, you know? I probably only want to focus those main variables, okay? So instead of talking about n by n, so can I simply talk about some simpler systems, okay, simpler system, like n0 plus n0 system, which is much lower in order. So the model reduction usually refers to you have a lower order approximation. Lower order approximation. So then you have a P of S is P naught of S plus delta P of S. Okay? So this is called lower order approximation. Okay? Lower order approximation. Okay? This is so in this case, even this P is precisely known. It's possible that this system is precisely known. And we on purpose want to make this model into a simpler model, and with all other parts into uncertainty. So whenever in the future you see this is uncertainty, I hope you should regard this one not just purely unknown factors. There are known factors. There are some on-purpose reduction of the model contained in the delta P. But when this is precisely known, how we can get a lower order approximation while I know what is the bound of my truncated. I just threw away those things. I know how much I threw away. Exactly, I know the bounds. And using this bound, we design the robust control. We use this one as a starting point to design the control such that the control is robust to this. Then life is much easier. Then you're working on this full big system. Make sense? Yes? So that's exactly the way we do. That's exactly what we do. So I hope from this explanation that robust control part makes sense. Okay? Makes sense. Okay. So if you do not learn robust control, that means the gap between you and the real world control problems probably is still quite big. If you learn robust control, probably is smaller. Okay, probably smaller. So one of the key part of this balanced model reduction usually is applied to the case when the P is exactly known. I want to make this one lower order model, and this is approximation error. I want to understand what is the precise bound of this. Okay, so to have very good solid mathematical discussion, then our foundation starting point is state space A, B, C, D realization of that one is called balanced realization. And after that, we need to introduce this balanced realization concept. Then we talk about Hankel norm. Okay? Hankel norm. Okay? And then we talk about truncation with none bounds. So I know this is the size of my system. I want to truncate this much. I exactly know how much the bound of the model I have thrown away. Okay? And that information is useful for robust control. But to do that, to have that exact knowledge about how big is the bound of the truncated model, it is a good idea to have a solid mathematics that we're going to use balanced realization, Hankel norm, truncation, all these type of concepts. And that's the main theme for today. And you may say, Dr. Chen, this is something interesting. You introduce why we learned this one beforehand. That's useful to connect and see the big picture. Yes, that's useful. But there was another reason I haven't told you. Okay, so people may say, so you remember the loop is called I plus Kp, right? Loop transfer function. Okay, this is input, okay, loop transfer function. Of course, you put the O here, then K is this side, right? So let's don't talk about this, but the point I'm going to make is you should from now on not only understand this is L is L0 plus delta L. Of course, you have uncertainty. And this uncertainty is not only from P, but also from K. I'm going to explain to you in a moment. Okay, so you may feel, this is my controller, why I have a delta K? Why I have delta K? Okay, so that is, in the end of the course, you are going to see, especially in project number 4, you are going to see the optimal and robust control that usually will lead to the K with very high dimension. Okay? But when you do real-time implementations, you probably want to implement a simpler K. But you dropped some of the accuracy here, and that one can be lumped. This one can be converted to delta P, right? Okay, you can convert. This is something you introduced in here, then can be lumped. So this is called controller reduction. It's called controller reduction. Controller reduction. So the model reduction we learn here applies to both this one and this one. Not only the model, but also the controller. And the controller, usually you got a controller, you just implement it, right? But in robust control, it's usually the case that this one is also too high an order, very big, like 40, the order is 40. You have 40 polynomial, okay? So then you have issues about numeric accuracy, your accumulation, internal state divergence, about your realization. So you probably want to do a model reduction for controller using approximated realization and along this size, if you know it precisely, this can be converted to your planned uncertainty. Then you redesign your system, okay? Then done. See what I mean? So that's another hidden reason you don't get explained in the beginning. Only in the end you realize that all the model reduction applies both to system as well as controller. Okay? So to start with, we are going to talk about So this is outline of this week's. This is something I didn't like. This is the bug from Microsoft. Really. Just a second. It should work. Why this guy is not working?
Is the projector muted, perhaps?
No, it's not. Not. It's on. Can you guys see? Oh, it's from my projector. This one. Let me do one more time. Video mute. Video power on. Screen up. Screen down. Mute. Unmute. That's not very good. You guys can see this? It's not very good. Why this is not working? When I do this, you see it's tangent. Let me do one more thing, then I'll give up. This one should work. It's not because of me, it's because of the projector I use. Okay, so you can see we have a lot of topics today. So can you see that? Okay. So probably I don't know.
You want me to call IT?
Yeah, you can call. So what we are going to do here is to review the linear system theory. Can you see that we start with definite equation, we do gradients, we do controllable decomposition, observable decomposition, and then to the balance realization. So until all these things are considered as linear multivariable control. Linear multivariable control. Okay? Linear multivariable control. So you can see from here, right? So that's good. Maybe let's do this way. Let's do this way. So I'm going to erase this motivation part, and what I'm going to do next is a study of linear systems. Okay. So starting from the spring of 2020, yeah, we are going to have 2020. We are going to have ME212 linear multivariable control. So this course is a much more detailed course. It's supposed to be a prerequisite course for ME212. Okay, 212. That's robust and optimal control. And there is also ME211. It's a nonlinear control. That will be a nonlinear control. So that will be offered perhaps 2021. Okay, 2021. And so that's basically ME2. So this is a 2019. So next one we are going to do 2022. So the projector of this one is not giving us anything. So I don't know why. You can go and work on that. Yeah. So everything is working. Is not this projector.
Okay.
Yeah, I did mute before, then I unmute again.
That's just kind of
Yeah. Okay, you go for it. So then you can see we are doing every 3 years, and then 2024. So this one will be 2020 spring. So then I think it's 2022 we'll do one more time. So this is the spring, okay? Spring. So these are the 4, okay? This is 4. This is the 4. Okay, so that's our advanced control sequence, okay? Advanced control sequence. So I hope you are familiar with Lyapunov function, okay? Idea, okay? So
I can put the screen
yeah,
down.
done, go ahead. So what we do is I have an x dot is ax, okay? So when we can see whether the system is stable, when we can see that. So of course we say that for all I, that the real part of the eigenvalue of A will be live in the left half plane, okay? Left half plane. So therefore all I. But that is for eigenvalue approach. Okay? But what if we use energy point of view? So Lyapunov function V is function of x, okay? That will bring x transpose t, x transpose t, x. So then this is becoming a quadratic form. And we use like half of this one, okay? So, but in general, you can do positive definite matrix. The P could be I, okay? In our previous case is I. So that is called Lyapunov function. Okay? So there are several conditions. One is V0 is 0 whenever, if and only if x is 0, okay? Then the second is the Vx is always greater than 0 if, always greater than 0, and for all x, okay? Not 0. So this is kind of like energy. So x goes to infinity, v goes to infinity. There's another one. V infinity is infinity. Okay. So these are considered as energy, right? Generalized energy. So now, if the system corresponding generalized energy will always decay, then we are going to say Vx dot less than 0 is always decaying. Then we say the system is stable. Okay, of course, we should say stable in the sense, of Lyapunov. So the people usually say that, oh, this V dot is equals to Q, while Q is less than 0. So which is a negative semi-definite, NSD, negative semi-definite. So together, this is stability. So based on that, if we do V dot, we're going to have X transpose P. So you do X dot here, and then plus X dot transpose P and X. Okay, so then you will have this is V dot. Then you want this one to be Q, and you replace this guy as AX. And you put this one is X transpose A. So in the end, you have X transpose PA plus, here you have X A transpose P and X. Okay, so this is still a quadratic form. So quadratic form, if we want to have a negative semi-definite, so you are going to write PA plus AP. So you will have PA plus AP is a Q less than 0. Then it turns out that,
Good.
what happened?
I just had to reset the projector.
Oh,
Yeah.
okay, good.
Yeah.
So restarted it?
Yeah.
Oh, good job.
Okay.
Okay.
Thank you.
Okay, good job, thanks. So basically, instead of looking at the eigenvalues, we turn this stability question into a Lyapunov function, saying that giving giving negative semi-definite matrix Q, can you find a positive definite matrix P to satisfy that? So this is called Lyapunov equation. So Lyapunov equation is based on this. So we are going to see it. So it will be very fast in the next. So good. So Lyapunov function. So basically that following Lyapunov function, instead of using P, I'm using X. Okay? So X, if A is stable, then the P, okay, the P can be written as integration of A transpose T and Q E. So remember here, we didn't say Q. What is Q? In this case, E equals minus Q, so the Q should be positive definite, okay? So this is a positive definite. So then X is positive definite. So this is equivalent to say that if Q is positive definite, then X will be also definite, positive definite, okay? If a semi-definite, positive semi-definite is like this, then it is a positive semi-definite. So if Q is a positive semi-definite, then we know that minus Q is negative semi-definite, right? So then Q and A is observable if and only if X is positive definite. Remember, X should be here, the P, okay? The P is the weighting we put in here, weighting we put in here, okay? So it has to be greater than 0. So all these proofs can be relied on this, what I call generalized energy concept. So this is more on the nonlinear control systems regarding the Lyapunov stability. But in linear system, we can use the same. Okay, use the same. So the proof is straightforward. So I'm not going to pursue this one further. It's in our textbook chapters. So then, if you have a positive definite matrix, you always can do this decomposition into C transpose C. Okay. So then you can always write. This is a correct form. Okay. Correct form. So X should not be singular. Okay. So similarly, you can decide, but this concept is from linear system. We don't have a C in here. We don't have a C. We haven't introduced the C in here. But the C is introduced from the Q. From the Q. The Q, you can do a decomposition of C transpose C. Okay. Then you see, oh, this C and A observable, Q and A is observable. Okay. So that kind of proof, I consider is linear system is straightforward, as I already told you. So then, so X is solution for the Lyapunov equation. Then eigenvalue of A will be less than 0. So that is a system is stable if X is positive definite and Q also definite. So in this case, I'm writing the Q in here, but they write the Q in here. They write the Q plus Q. Okay. Plus Q is 0. Then that is actually equals minus Q. Okay, minus Q. So it's the same idea. If your Q is positive definite, okay, that means your V dot will decrease. The V dot will decrease. Okay. A is stable if this positive definite, and this is also positive definite. So these are just, I think we even have derived this. Okay, let's go quickly. So the reason we are trying to introduce the Q and the C, remember, Q equals, this is a Q, okay? This is a Q. So it is possible that, so the Q is called Gramian, okay? So AB is controllable if the controllability P Gramian satisfied. This one is 0, okay? So this one we talked about using the Q to satisfy that, and then you put this one as C transpose C. Okay, C transpose C. So then if this C comma A, using C as an output matrix, then you are going to have observable form. So then Q solution from the Lyapunov function will be your observability Gramian. Okay? So you can see, you can put all of things starting from Lyapunov stability from LTI system here, and general energy will not, will decrease. Then from the Lyapunov function, you can introduce the Gramians, okay? Introduce the Gramians. Similarly, you can do controllability Gramians. So that, okay, that, to make this one 0, okay? I want to remind you, because it's confusing, okay? It's very confusing. When I was a student, I also feel very confusing. So let me highlight a few things for you, okay? The choice of the P is infinitely many. There's so many choices of P to argue about stability. Okay? There are so many choices of Q. Okay? So either giving P, you can find a Q, or giving Q, you can find a P, right? So there are so many choices. But there is a very unique choice that if you are doing something like VU, here is Y is CX, okay? If you somehow choose the Q is C transpose C, okay? C transpose C, okay? So remember, B is like A is n by n, B is n by n, and C is Q by n, right? Q by n. Okay? So C transpose C will give you what? Well, Q, so is n by n, right? And remember, B transpose B is also n by n, right? N by n. So these, if I choose Q to this way, or I choose Q to this way, will have some special meaning. Will have some special meaning because when we use this one to put in Q, then we solve the P. This P has a different name. This P is also called controllability gradient or observability gradient. Okay? Okay, so I hope this is not very confusing, huh? Very confusing. But remember, the controllability gradient and observability gradient was never introduced in this way. Okay? It was not introduced in that way. If you go back to the definition of controllability and observability, then you will see the gradient is because of the solution of the system, the existence, according to the definition. Okay? So with that, I hope everybody here don't feel surprised. The gradients are connected to the Lyapunov equation in such a way. Okay? So let's focus on that. So only when the system is stable, this is important, okay? Only when the original linear time invariant system is stable, then you can say that the solution of the Lyapunov equation is happens to be gradient, okay? Then there are two possibilities. One is you choose Q like this, one is you choose Q like that, okay? So that's a basic idea. If you have A, B, C, then you can talk about using the Lyapunov equation so that choosing a special Q, okay, so you have P. I don't like this Q here. You should not use Q here. So I use my Q in my sense, okay? So this is also P, okay? This is also P. But in this textbook, they use P to denote controllability gradient, using Q as observability gradient. But in the Lyapunov equation sense, P is all X, he used the X, okay? The solution. So then this is the Q, okay? This is the Q, a special form. All these can be easily derived. And I think it's in the textbook they derive all the details. The reason we introduce this one is to talk about balanced realization. Okay? Balanced realization. So what we are going to do next is to tell you that I have a transfer function matrix G of S. Okay? Then I have so many infinitely possibility of having A, B, C, D to do a realization, okay? So you have A, B, C, D is A state space realizations of a transfer function matrix. Be careful about this term here, A, but totally how many? The number is infinitely many realizations, okay? Realizations. So we want to think that out, okay? So one is in the controllable decomposition form, okay? So again, you have a symmetric matrix P, okay? We didn't say this is a Gramian, okay? So the P1 part is non-singular and others are zero. Okay? It's always possible you write this way if it is not fully a full rank. Okay? So then we satisfy Lyapunov equation. So then you also make a partition of the A and B and C and in two parts. So then, so you can see that. You pick up A11, pick up B1, pick up C1, and D1 also. Okay. So you basically put this P because of this P, you know. Okay. Then you can see this is also a realization of G. Okay. So in this case, if A11 is stable, then A11B will also be controllable. So this is from this form A, B, C, D to this form, okay, is by rearranging them, and then you will see this is also a realization, but it with smaller dimension. So smaller dimension. So this dimension is smaller than this, okay? And because when you do realization, there's a possibility that the realization may not be minimum, okay? So that's why we need to talk about a minimum realization. So minimum realization is, it must be a controllable, okay? Controllable form. And the same thing applies to, so this is called controllable decomposition. So controllable decomposition. So you do arbitrarily A, B, C, D, it may happen that it is not minimum, okay? So there are some redundancies. Then you have to remove those zeros, okay? I think the proof is just simple matrix partition, okay? That's not very hard, okay? One of the ideas we do here is to move, to make this one 0 first, okay? And make this one 0. Because the partition of this equation, the Lyapunov equation, and you can do a partition, put the P in here, and these are zeros. Okay, these are zeros. So B2 is 0. B2 is 0. And this one, P1A, this is 0. That means this one. This is 0. So the realization of this one after partition will become this, and this one is equivalent to this. So that's from non-minimum to minimum. Okay? The same thing we can do for observable decomposition. Okay, observable decomposition. And the reason is we have the C, then we can check my Q. Okay, you can solve the Q, but it may not be a Gramian. Okay. The same thing we can do the partition, something like this. So it's also a realization. So in this case, if C1, so this one C1 and A11 is observable. If the A11 is stable, okay. So we have seen that we can remove those redundancies in P and Q, to make them controllable or observable. I said or, okay? So what is N? What is both controllable and observable? That is this called balanced realization. So what does that mean is of course, we have a gramming of controllability and observability gramming in here. Then we have P, let P equals Q. Okay, that's Q. Okay. Then the state space realization is called internally balanced realization. And the P and the Q can have a diagonalized, and this sigma 1 and this sigma n in the Q. This equal meaning they have similarities transform, so it's all diagonal. And those diagonal sigmas are singular values has a special name in this context called Hankel singular values. Okay, Hankel singular values. So that is what we call balanced realization, internally balanced realization. And balanced realization are both controllable and observable, and P equals Q equals that diagonal. That is called internally balanced. Okay? For equally observable and controllable. So that is balanced realization mean to make this P and Q or diagonal. And the diagonal is called Hankel singular value of this original system, G of S. And this realization is unique. You only have one such realization. It's called minimum balanced realization. Okay? Of course, balanced realization are minimum realizations. Okay? So there are two extreme cases. One is you set the gramming of controllability gramming as I, then you have Q actually will be sigma squared. Okay, that's interesting. And the same thing is true. If you put Q is I, then your P is sigma squared. So this is by kind of scaling. What do we mean scaling? That is, you always can scale your system states to make this one happen. Okay, to make this one happen. Okay. So, but that's not quite frequently used. The most frequently used is this one, and it gets sigma 1. Okay, and sigma 2 and sigma n greater than 0. And P and Q, remember, they are Gramians and symmetric and positive definite. Okay? So how to compute? I gave a G of S, then can you come out A, B, C, D for me? That is uniquely balanced minimum realization. Equally controllable and observable. How to do that? Here is the step. Okay? How to compute that. So first of all, you need to find, so basically you need to find a P and a Q and find a matrix R, make this decomposition, okay? Then you diagonalize RQR, then you have this one, okay? And of course the U is the unitary matrix to diagonalize everything of this one. This is a positive definite. So then you can see that this similarity transformation T becomes becomes like this. So then you put in the P. This is called similarity transformation. So make that one, you end up with this. Okay, which should be diagonal. Okay, for the diagonal. So in this case, you start with A, B, C, D, what you should do next? First of all, you need to do a minimum realization, okay? Minimum realization. So minimum realization says that your P cannot be contain zeros like that when you do diagonalization. So you always can have non-zero. Okay, so that is called minimum realization. So this is a minimum. Okay, this is a minimum. The same thing for observable decomposition. So the balanced one is when P is Q and is diagonal. Okay. So then, what we are going to find out is T. That T is called similarity transform. To transform the minimum realization to a balanced realization. How? How? So we can go backwards. Okay, backwards. So so given this one, we choose the P, any P, Q, then we get this T. So the inverse of the T should be R transpose U, and sigma square, okay, sigma square, root, okay. And you also make this P will make the P diagonalized, okay, diagonalized. And this also makes Q diagonalized, okay. So in general, the P and Q can be positive semi-definite matrices. So you always can have this P and Q to make them as diagonal matrices with diagonal matrices and a positive definite. But good news is in MATLAB you don't have to manually compute these, and good news is you can do it in a simple command, okay? And it's called balanced realization. It's called BAL, real, okay? Ball real, balanced realization. We'll review that later, okay? So it's ball real, okay? So this is balanced, this is a real, okay? And then they will give you sigma. This is sigma is diagonal. So the vector of Hankel singular values. And this T inverse is the similarity transform. Okay? So this, so the G, okay, G has a name. G is an LTI object. So you give the LTI object, this is state space realization, give A, B, C, D. So you put in here, balanced realization will come out with T, come out with sigma matrix, and this GB is another LTI object, an LTI object that is balanced. So this is balanced realization, okay? Balanced realization, okay? So, because this is balanced and it's also ordered, let me go back. So this is also ordered, okay? So be careful. Okay? So this one greater, so it's also ordered, okay? Ordered. And remember, singular value meaning is strong cross-effective connection. So that means the smaller, that means it's less important in this MIMO cross-effective. Okay? So there's a possibility we can say, hey, I want to cut off everything greater than R. Okay, let's say R is a reduction order. Of course, R less than N. I only want to keep the first R. I want to drop the last R plus 1 to N. So that is called balanced truncation. And you truncate those Hankel singular values. Okay? It's called reduced order. So you have a balanced, Okay, balanced, okay, and model reduction. Okay, balanced model reduction. So basically, you have a G. The G will have a balanced realization. You have GB. Then in the GB, sigma, you drop the you keep 1 until 2R, or delete the rest. Then you have a reduced model. The model reduced, okay? Reduced. So this is called reduced order, okay? Reduced order. And they can automatically to tell you that those reduced, those truncated ones, and will result how big the mismatch between the reduced model and the balanced realization model. Okay? So this model and this model, they are the same dimension, okay? But they are balanced. This is balanced. Because the original one, you do the realization, it may not be minimum, it may not be balanced. So internally, they will do this automatically for you. Okay? So that is connecting to, so the size of this one is truncating those less controllable, less observable states will not lose much information about the system. That's interesting. That's interesting. So the first R probably is representing the majority of the dynamics. The others are trivial. It's hard to control, it's hard to observe, why bother? Just truncate. Okay? And that's exactly we are saying that when you truncate, you're locked into the uncertainty, then we focus on our robust control design so that the robust control will guarantee my performance and stability are robust with respect to those truncated ones, then life is easy, right? So that's the beauty of robust control. And this is also beautiful that give you very solid foundation of truncating or reducing the model order with peace of mind. You have exact knowledge about how much you truncate, okay? Truncating. So here are the beautiful parts, okay? Very beautiful. When I first seen this one, I was shocked. So we don't consider D in here, which is okay, so it means we are in RH infinity. It's rational, strictly proper, stable, and transforming matrices. Balanced realization, okay? So ABC is balanced, meaning it's unique. Balanced realization is unique. Minimum realization is not unique yet. Make sense? Okay? So this is unique. Balanced realization. I think you should say is the balanced realization. It's not a balanced, right? Because this is unique. So then you have diagonal of this one, and this could be a block. Okay, it doesn't matter. You have a repeating sigma, and then everybody you know that this is ranked like this. Okay, ranked like this. So you have a multiplicity S1, S2, Sn. That doesn't matter. Okay. Then we know that according to the balanced realization concept, we have put this one as Q, put this one as Q, then we have the same sigma is my Lyapunov equation solution. So it's P and Q and the sigma, okay? And what we are doing here is, these are the beautiful ones, let me show you. Okay. So first of all, the maximum singular value, maximum Hankel value here, Hankel singular value, sigma 1 here, is always less than infinite norm. So infinite norm is greater than or equal to that. And the infinite norm is smaller than this impulse response function integral, okay, to norm. So basically, you give impulse, the system will respond and decay to zero. Now, what's the area of that? Is this thing? Okay, impulse. The system will react to the impulse and then get to the rest again. So that kind of area in that impulse response is finite. But the area is greater than this one, G infinite. And what is the bound of that? It's beautiful. So if bound is less than 2 times of the all Hankel norm added together. So this is beautiful, right? Beautiful. And this is impulse response. When the control U is impulse. Okay? Impulse. This is C, E, A, T, and B. This is impulse response of the minor system. Okay? I hope the proof, I think, is not going to be interesting here to us. We can read the textbook for proofs. But this is important. But this is important, interesting, important result. So this is a G, you know exactly G. You want to use a simpler model, but you want to use this balanced model truncation idea to make it a reduced model with a truncated part, okay? A truncated part, okay? So I put the degree of GR, the degree, less than R, okay, less than R. I hope this can be minimized, okay, this difference. Real model, full model, and reduced model difference is computable, okay, computable. So now we can use what we have learned in here, okay, learning here. So you split the system in 2 parts. One is 1 to R, that's we want to keep. R plus 1 to N, that's we want to truncate. And we also know the notation here, we use this decreasing manner. So we're doing kinds of, so the next question is, how big is this? Okay, how big is this? Okay. How big is this? So the next slide will give you this beautiful, beautiful result. Okay. So it doesn't matter, we have multiplicities for each sigma I. Okay, I know this multiplicity add together is n, not a problem. So the reduced model is kept like this. It's still balanced and asymptotically stable. And these are the most useful ones. I love this one. Okay, I love this one. This one. Okay. So this is the delta, the truncation error. Okay. The thing you truncated, I want to know the worst case norm. Infinite norm is the worst case norm. That is upper bounded by all of them add together times 2. Okay? So this is called Hankel singular value. They are so useful. Okay, so useful. And there are some further results. If the original system, okay, this is G infinity is high frequency gain. Then usually it's 0. Okay. It should be this. It should be less than 1 until the end. The whole thing. Okay. So the whole thing. Okay. And the last one. Okay. This one minus last one, it will be exactly 2 sigma n. So these are very interesting results, and I believe especially this one is very useful for us to design robust control. Okay. This can be proved rigorously, and we're not going to pursue that. So in the end of the day, we are basically trying to check the difference of this maximum singular value of this omega. Okay, and for all omega actually will be like this. Okay. Usually we simply use this result for our design. So this result for our robust control design. There isn't worked out the example here to show that the bound is actually quite tight. Okay, the upper bound is very tight. Okay, it's very tight, and so if you have a SISO system, this is a single input, single output system, and you have n low-pass filter type of thing add together in parallel. So you have AI, BI, and how to do. So the B matrix is n by 1. Is n by 1. This is n 1 by n. And then this one is a diagonal of this one, okay? So the P and Q will be like this, okay? And this infinite norm will be the sigma of them, okay? And then this G0, okay? G0. Add all this when S is 0, so it's this one equals 2. So it's actually equal, okay? Very tight. So Hankel norm is something not in the textbook until maybe from 1990s. So it's kind of a new angle to look at this one. There was a paper in International Journal of Control, IJC. That paper is called Hankel norm. Written by Case Glover. His name is called Case Glover. Okay, Case Glover. And I think he's one of the people contribute a lot to this topic. And if you get read to the original 90-some pages, IGC paper, you feel like, wow, that's a long journey. Because finally we are using this tool, but initially people get a long journey to get to the point. So Hankel singular value is the way to go. Balanced realization, balanced truncation, that idea is the way to go. And now you start to appreciate state space is useful. Okay, state space is useful. Even we start with state function matrix. Okay. So you can see that the estimation of the norm, can be loose for a system with Hankel singular value close to each other. So sigma r plus 1 is small. Okay. And the bounds can be big. So sometimes it's big, sometimes it's small. So can be tight, and it could be loose. Okay, that's the message. But there's no better way than this so far. About when you truncate, then what's the size of the uncertainty you introduced. The rest of things is to add WO and WI, and input and output into that balanced model reduction. So you basically have original G transfer function matrix, you have W weighting function, weighting filter matrix. Each of them will have ABCD realization. Then the composition will have this. And from here you can do this, okay? You can do this. Then you can have that kind of Gramian again, but it is in this format, because it may not be minimum, okay? It may not be minimum. So there's some tedious derivations here. But however, in a more general weighted balanced realization, you can use this command called reduce with those weights. Okay, with those weights. So that is model reduction in the frequency and domain weighted filtering. And we have a ready command to do the job. Okay? We're going to continue the discussion about relative reduction. Okay? Sometimes what we said so far is called additive. Okay? G plus delta G, right? G plus delta G. The uncertainty we talked about is G plus delta G, the plant with plant uncertainties, it's called additive uncertainty. Well, what if your uncertainty is relative, is multiplicative like this, okay? So, but it also can be transformed into a G inverse like that, okay? But there are some different arguments here. We are going to start to talk about this next time. So with that, we can finish today. And again, model reduction, balanced model reduction, it turns out like it's a fundamental technique you should have in robust and optimal control. Because when your system is too complicated, you should say, let me try balanced reduction. Truncate those small Hankel norms, Hankel singular values. So another good habit is giving a system, probably you should check all the Hankel singular values. And there is a command to do the job automatically, okay? Just call Hankel, okay? They will give you all this order Hankel singular value. So if you see this biggest one, smallest one, then just like 2 orders of magnitude, so you should consider to truncate, okay? So, but if they say, oh, all the way same size, okay, probably you should not truncate, okay? That will give you very good insights, justify why you shouldn't use model reduction. Okay, so see you Wednesday, and I'm going to maintain office hour until 3:30 today. I will be here until 3:30. Please catch me in my office 3:30 if you want to talk to me.